Hey everybody, today's lecture is about graph isomorphism. I like that the textbook has some etymological information here. They mentioned that the Greek word iso, well, do they say it all? Iso is a Greek prefix that means equal. Morph is a thing that means shape, and so isomorphism is a thing that lets you know things have equal shape. I guess that's close enough. Yeah, so I'm going to read this definition to you. I've forgotten what page number I'm on. Perhaps it's in the scan. But I zoomed it in so much that I can't see where the page numbers are. 676, okay. 676 in the book, definition 10.4.1. Don't expect to hear or even stare at this definition, try to memorize it, and really understand it. We're going to do some other playing around with examples that I think will make it clear what's really going on. But here we go. Let G and G prime be graphs with vertex sets V of G and V of G prime. So that's pretty standard, right? We've got two graphs and their respective vertex sets. Yeah, they also have edge sets E of G and E of G prime, respectively. You say G is isomorphic to G prime if and only if. It's important that that's a two-way street, if and only if. There exists a one-to-one correspondence. Oh, they say, wait, there's two of them. If there exist one-to-one correspondences, little g from V of G to V of G prime, and little h goes from E of G to E of G prime. These are functions, right? But the fact that they've said something a little better here, they're one-to-one correspondences. That's because they're functions that send one thing to exactly one other thing. They're particularly nice that way in a generic function that doesn't have to happen. Okay, wait, I got so far. If and only if there exist one-to-one correspondences, G from V of G to V of G prime, H from E of G to E of G prime, here's the rest, that preserve the edge endpoint functions of G and G prime, in the sense that for all V in the vertex set VG and E in EG, and this is the kicker, this part that's displayed underneath, V is an endpoint of E if and only if G of V is an endpoint of H of E. That is, corresponding vertices are hooked up to corresponding edges. And these maps G and H give you the correspondence. Right. So let me run an example, in CoCalc. I think I've meddled with these examples, so let me rerun it and see what it looks like. That's not so bad. I'm going to hide the stuff that defined this graph. That's just some CoCalc stuff to get a graph. And there's another graph. The first one I called G1. This is G2. And let's display it. Okay, and let me just hide the definition again. So hopefully we can get both of these graphs on the screen at the same time. Just about. All right. So are they the same shape? That's our big question. If you look at them, they have similar features. They have certain things that are kind of similar. For instance, you might notice they both have a multiple edge at between a couple of the vertices. There's a loop on this one, and there's a loop on this one, and there's this like dangly bit here, and a dangly bit here. Now these vertices, if I mouse over them, you should see a little pop-up that tells you what the, I hope that in the overlay pane actually shows up in the scan, in the saved video. But anyway, I'm pointing at vertex 0 here, then they go counterclockwise. This is 1, here's 2, there's 3, here's 4, and then this 5 is all by itself. And this one, 0, is also at the top. In fact, they go in the same order. 0, 1, 2, 3, 4, and 5. They're not identical. For instance, this is 5 over here that is at the end, and this one is called 4 over here. That's dangling off the end. So they're not the same, but maybe the mapping, the little g that was over there, is that 5 gets sent to 4. That could help. In fact, these are identical graphs, and you can, I shouldn't say identical, isomorphic graphs. And we can move things around until we believe that. So the thing that I would say is this node up here at the top that has a loop, that's a very distinguishing feature. None of the other vertices have loops. So I'm going to move that to the top in this other graph, and then move all this other junk back out of the way. Looking more similar now? Notice how the double edge is just one away from where the loop was. So I can make them look kind of alike. This thing isn't where it should be, but if it was there, it would be good. And how about I try to move this guy to here, more or less? And then lastly, this guy goes upstairs. Yeah. Oh, I think I've just found the isomorphism. I found essentially by visually editing the graph, I've put the vertices of the second graph in the position so that they correspond to vertices of the first graph. So our mapping should be vertex 0 maps to vertex 2. Vertex 1 goes to 1. Oh, well, 1 and 1 were the same. This one is 0 down here. Upstairs it's 2, so we need 2 goes to 0, etc. So if you can keep that kind of imagery, any way to say it, imagery in mind when you are thinking about isomorphism, it'll work for you, really. Use your visual thinking to say, oh, I need to move this thing over there, and you can often see your way clear to figuring out what the isomorphism should be. All right, so I need to give you an example that's graphs that are not isomorphic, so that we get the idea from both sides, right? Sometimes it'll be possible to do what we just did. Other times, not so much. Okay, so here's another pair of graphs. I made just a few changes to the graphs that we were looking at a second ago. Question is now, are these things isomorphic? Now, okay, so one of the features you see is that edge that has a loop, node that has a loop on it. We have that over here in the lower graph as well as the one on top. So that's fine. I took away the multi-edge, but I did that in both graphs, so that's a good thing. I'll point out, though, that would be something that you could check for real quick. If one graph has a multiple edge, a set of parallel edges going from between the two different, but darn, saying that badly. This, right? The two vertices that have a pair of edges between them. If that happens in one graph and it doesn't happen in the other graph, there's no way you could find a mapping that has that property that was spelled out in the definition. So if you have multiple edges, both graphs need that. All right, so can we move? Let's keep the top one fixed and try to move the bottom one around until they look the same. So I'm going to again put the loop at the top and move the other junk down out of the way. I don't know what to do with this piece now. Well, let me try to put this part that looks like a tail on it over where it belongs. That's pretty good. This other guy is down here, though. It should have been down. So far, it's not looking like I can do it, but I need a convincing reason to say, oh, it's a fool's errand, stop, rather than maybe you should keep just trying because you haven't figured it out yet, but there's some reason, there's some hope that you could, get smarter and figure it out. So what is that convincing reason? Well, any such convincing reason is what's known as a graph invariant. An invariant is a number or even a Boolean thing, a true-false kind of question. But a thing that, if it's true in one graph, then it will be true in another graph that is isomorphic to it. And what we've got here is a case where one of the simplest graph invariants will tell you there's no hope here. Look at the degrees of the vertices in this top graph. This guy up here that has the loop has degree 5. Remember, the loop counts twice in its degree. Then we got a 2 and a 3 and a 2 and a 3 and a 1. Down below we have a degree 4 and then a 2, a 3, a 2, a 4, and a 1. Could these be the same? Well, nobody down below had degree 5, did it? So the top graph has a node of degree 5 and the bottom graph does not. Case closed. They cannot be isomorphic. Right, so here's another pair of graphs, and they have a lot of the features that you're going to need to be able to say that things are isomorphic. Let me name a couple of invariants that they do share, that they have in common. First off, we don't have that issue about degrees, because every degree in each of these graphs is 3. You see how each node has 3 things hooked to it? And down here, each one has 3 coming out of it. It's a little hairy in here. There's this weird thing with the lines crossing, but that's not a vertex where they cross, right? So yeah, everybody's degree 3. So we don't get off easy on this one. There's no, quick way out. Let me point out some other things that are invariants that these guys share, but you might not have even thought to check for this. But look how many edges are there. There's 12 in each of them. Count them up. There's 12. There's 8 vertices in each of them. Look, if it has a different number of vertices in the top graph than it has in the bottom graph, you're done. You don't have to worry about it, because you will never find a one-to-one function that takes a set of one size to a set of the other. That's what one-to-one is all about. It actually is what's used as kind of the definition of things being the same size. All right, so we're good on those counts. We've got all the same degrees, all the same, that same number of vertices, the same number of edges. It's looking good. But there's this, I don't know what to call it, this little twisty bit that happens because of the particular embedding in this graph, and I've got to untwist that so that I can see the top one looks exactly like the bottom. So just untwist that part. Oh crap, well it twisted these now, so let's just fix that, and then now these are twisted. I'm not sure if maybe I need to put some different cycle of 4 things in the middle, and maybe for instance these 4 could be the outside stuff, and then I'll move this other junk into the middle. It's still got a twisty bit in it, but that's okay. I can untwist that with. Okay, it is starting to feel like maybe this isn't going to work. What do I do? Well, I need, again, an invariant that one graph has and the other graph doesn't, right? Some property that I can say that graph has blah and the other graph doesn't have blah. So what is it? There's lots of things that you can check for. In this one, the easiest thing is cycle length. This graph up here actually has nothing but even cycles in it. You see how there's like a 4 cycle there, a 4 cycle in the middle. There's like a trapezoidal shaped 4 cycle around the top and around the bottom. It's not just 4 cycles though. For instance, here, let me pull these guys out and bring them to the bottom. Go right around the outside of it now, and that is 6 things. Heck, if I bring these guys down and put those guys up higher, there's a cycle of length 8 in that graph. Well, this graph, I think it has cycles of length 8, but what it definitely has that the other one does not is an odd cycle. There's a cycle, wish I had a good way to draw this. I'm going from vertex 4 to 7 to 2 to 1 to 0 and back to 4. That was 1, 2, 3, 4, 5 edges. There's no odd cycles up here at all. They're all even. To show you that that's the case, I'll bring in another invariant actually. There's a question of whether a graph can be embedded such a way that the graph's nodes fall into 2 camps, so to speak. with all the connections going between the camps. So I'm just going to grab one node and bring it over to the far right side. I think that one will be fine on the far right side. Anything they're connected to, however, needs to go to the other side. Cool. And then, well, looks like this one could be brought over here. Is there anything else on this side that nobody on so far is connected to? Yeah, this guy. Bring him over there, and then I don't know how to sort this all out, but well, anyway, you see how this is in two camps with the stuff on the left and the stuff on the right. Nobody's connected to anything in their camp. All the connections go across between the parts. This is called being bipartite. This graph is bipartite, and that's why I know there's only even cycles in it. If you have a bipartite graph and you have a cycle, you have to end where you started, right? So you have to come over and back and over and back, and you have to end with a back, right? You have to do those moves, go from this side to the other, and then return if you're going to land back on the node you started at. So you'll have some even number of edges in your cycle. This graph is not bipartite, and you can tell that right away because of the odd cycle. Let me just modify it to make the odd cycle maybe more obvious. If I bring the edges that are involved in the odd cycle to the outside, 1, 2, 3, 4, 5 of them, and with 5 edges in a cycle, there's no way we can divvy these things up into two opposite camps like that. There will always be well, there's always be some connection between the groups. That's what the problem with oddness is there. All right, so we'll need to make a nice list of graph invariants and kind of get used to playing the game of locating them, things about a graph that you can say, okay, that one has it and that one doesn't, to show things are not isomorphic. When things are indeed isomorphic, it turns out to be, honestly, usually very easy to see that they're isomorphic. So let me give you an example next that's a pretty big, complicated graph, and yet we can just knock out the isomorphism quickly. Right, so the graph I had in mind is a thing called the Peterson graph. It's actually got a really interesting construction. You start by looking at K5, which has 10 edges. And then for each edge, you make a node in the Peterson graph. So each one of the nodes that we're looking at actually corresponds to an edge over in a complete graph with 5 nodes. And then you hook 2 edges together, well, nodes in this case. You hook 2 nodes if the edges they represent in K5 don't share anything in common. And if they do share something in common, then don't hook them up. And you get this really pretty graph. I think it's pretty, although it may look like a satanic symbol to you. And I'll tell you that this is exactly the same graph. They're isomorphic. Right? But man, you look at this. This is 6-fold symmetry, right? It's got a hexagon around the outside, and there's 3 things around 1, but this one is all 5-fold symmetry. It doesn't seem like they should be the same, does it? So run through our invariants that we've learned so far. Do they have the same number of vertices? Yes, they do. They both have 10. This one's a little harder to count, but that's 10 too. Do they have the same number of edges? I believe it's 15 in this one. There's 5 around the outside, there's 5 in this star in the middle, and there's 5 that go between the outer part and the inner part. So 15 there. I don't know if I want to count these. There's 6 around the outside, and then 7, 8, 9, I don't know how to count these. 6, and then there's X's, 7, 8, 9, 10, 11, 12, and then 13, 14, 15 from the middle. So yeah, they're the same. Another way to have resolved that would have been to go, well, what are the degrees of the vertices? They're all degree 3, and they are all degree 3 in both representations, so that's not going to get us out of it. Maybe they can be put into correspondence. If so, then we have to figure out, where does vertex 0 end up down here? Now, maybe there's a vertex 0 already. Is there, are they numbered? I think that's vertex. No, that's a 6. That's a 9. Where's a 0? There's got to be a 0. Is this one's? It came up for a second. That's 0. So I'm going to put 0 at the top. Maybe they'll match. There's 2 edges that are hooked to 0 around the perimeter of this thing up here. I'm going to get that pentagon. And then there's another one that is just below it. So I'm going to try to move things a little at a time until I make this other graph look like the one above. Great. So I need to have a pentagon that's going to be the outside. Well, I'm seeing 5 nodes. Can't seem to grab that one. Let me just push the other stuff randomly to the inside. You see the 5 are on the outside now? That's starting to form a pentagon. Can I get the star that happens in the middle to happen for us over here? Well, all these ones that have a connection to that outer ring, they need to be put in a position so that they are next to the thing that they're connected to. Oh wow, look, it's starting to just form. Now, it is, wow, it's just amazing, isn't it? I mean, you can tell it's not quite identically the same shape, but modular just morphing things around a little bit, we could make it happen. And this is, I'll be honest, I was cheating. See how I said Peterson equals graph.Peterson graph? Well, that's what I did for this one too. So I knew right in advance that they were the same. I just took the second one and moved it around to a new embedding. And now for you, I was just showing you undoing the work that I previously did. But I've done something interesting, haven't I? 0 went to 0. Did 1 go to 1? Well, that's a 5 there. So what I have done here is put the graph in correspondence with itself in a one-to-one fashion that preserves the adjacency relationship. So that's a really thing. Of course, a graph is isomorphic to itself, but usually just in one way, right? Just send all its vertices to all its vertices and don't change anything. This graph has sort of extra symmetries, what are called automorphisms. You can map this to itself and move things around and still have it be the same graph. That's kind of neat. And well, it's partly about the way the thing was defined, but yeah, I guess I just think it's cool that you can do a thing like that. All right, I think that's probably a good spot to stop. So we'll see you tomorrow.